Elementary particle, Wikipedia audio. In particle physics, an elementary particle or fundamental particle is a particle whose substructure is unknown, thus, it is unknown whether it is composed of other particles. Known elementary particles include the fundamental fermions, which generally are matter particles and antimatter particles, as well as the fundamental bosons, which generally are force particles that mediate interactions among fermions. A particle containing two or more elementary particles is a composite particle. Everyday matter is composed of atoms, once presumed to be matter's elementary particles, atom meaning unable to cut in Greek, although the atom's existence remained controversial until about 1910, as some leading physicists regarded molecules as mathematical illusions, and matter as ultimately composed of energy. Soon, subatomic constituents of the atom were identified. As the 1930s opened, the electron and the proton had been observed, along with the photon, the particle of electromagnetic radiation. At that time, the recent advent of quantum mechanics was radically altering the conception of particles, as a single particle could seemingly span a field as would a wave, a paradox still eluding satisfactory explanation. Via quantum theory, protons and neutrons were found to contain quarks, up quarks and down quarks, now considered elementary particles. And within a molecule, the electron's 3 degrees of freedom can separate via the wave function into 3 quasi-particles. Yet a free electron which is not orbiting an atomic nucleus and lacks orbital motion appears unsplittable and remains regarded as an elementary particle. Overview. Around 1980, an elementary particle's status as indeed elementary and ultimate constituent of substance was mostly discarded for a more practical outlook, embodied in particle physics standard model, what's known as science's most experimentally successful theory. Many elaborations upon and theories beyond the standard model, including the popular supersymmetry, double the number of elementary particles by hypothesizing that each known particle associates with a shadow partner far more massive, although all such superpartners remain undiscovered. Meanwhile, an elementary boson mediating gravitation, the graviton, remains hypothetical. All elementary particles are depending on their spin, either bosons or fermions. These are differentiated via the spin statistics theorem of quantum statistics. Particles of half-integer spin exhibit Fermi-Dirac statistics and are fermions. Particles of integer spin, in other words full integer, exhibit Bose-Einstein statistics and are bosons. Particle data group. Notes. 1. The anti-electron, E+, is traditionally called positron. 2. The known force carrier bosons all have spin equals 1 and are therefore vector bosons. The hypothetical graviton has spin equals 2 and is a tensor boson. Whether it is a gauge boson as well, is unknown. In the standard model, elementary particles are represented for predictive utility as point particles. Though extremely successful, the standard model is limited to the microcosm by its omission of gravitation and has some parameters arbitrarily added but unexplained. According to the current models of Big Bang nucleosynthesis, the primordial composition of visible matter of the universe should be about 75% hydrogen and 25% helium-4. Neutrons are made up of 1 up and 2 down quark, while protons are made of 2 up and 1 down quark. Since the other common elementary particles are so light or so rare when compared to atomic nuclei, we can neglect their mass contribution to the observable universe's total mass. Therefore, one can conclude that most of the visible mass of the universe consists of protons and neutrons, which, like all baryons, in turn consist of up quarks and down quarks. Some estimates imply that there are roughly 1080 baryons in the observable universe. The number of protons in the observable universe is called the Eddington number. Green, Brian, Elementary Particles, The Elegant Universe, Nova, ParticleAdventure.org, a well-made introduction also for non-physicists, CERN-Courier, Season of Higgs and Melodrama, Pentaquark Information Page, Interactions.org, Particle Physics News, Symmetry Magazine, a joint Fermilab/SLAC publication, Sized Matter, Perception of the Extreme Unseen, Michigan University Project for Artistic Visualization of Subatomic Particles, Elementary Particles Made Thinkable, an interactive visualization, allowing physical properties to be compared. In terms of number of particles, some estimates imply that nearly all the matter, excluding dark matter, occurs in neutrinos, and that roughly 1086 elementary particles of matter exist in the visible universe, mostly neutrinos. Other estimates imply that roughly 1097 elementary particles exist in the visible universe, mostly photons, gravitons, and other massless force carriers. The standard model of particle physics contains 12 flavors of elementary fermions, plus their corresponding antiparticles, as well as elementary bosons that mediate the forces and the Higgs boson, which was reported on July 4, 2012, as having been likely detected by the two main experiments at the Large Hadron Collider. However, the standard model is widely considered to be a provisional theory rather than a truly fundamental one, since it is not known if it is compatible with Einstein's general relativity. There may be hypothetical elementary particles not described by the standard model, such as the graviton, the particle that would carry the gravitational force, and sparticles, supersymmetric partners of the ordinary particles. Common elementary particles. The 12 fundamental fermions are divided into 3 generations of 4 particles each. Half of the fermions are leptons, 3 of which have an electric charge of 1, called the electron, E, the muon, mu, and the tau, tau. The other 3 leptons are neutrinos, nu, E, nu, mu, nu, tau, which are the only elementary fermions with no electric or color charge. The remaining 6 particles are quarks. The following table lists current measured masses and mass estimates for all the fermions, using the same scale of measure, millions of electron volts. For example, the most accurately known quark mass is of the top quark, T, at 172.7 GeV/c superscript 2 or 172,700 MeV/c superscript 2, estimated using the on-shell scheme. Estimates of the values of quark masses depend on the version of quantum chromodynamics used to describe quark interactions. Quarks are always confined in an envelope of gluons which confer vastly greater mass to the mesons and baryons where quarks occur, so values for quark masses cannot be measured directly. Since their masses are so small compared to the effective mass of the surrounding gluons, slight differences in the calculation make large differences in the masses. There are also 12 fundamental fermionic antiparticles that correspond to these 12 particles. For example, the anti-electron, E+, is the electron's antiparticle and has an electric charge of +1. Isolated quarks and antiquarks have never been detected, a fact explained by confinement. Every quark carries one of three color charges of the strong interaction. Antiquarks similarly carry anticolor. Color-charged particles interact via gluon exchange in the same way that charged particles interact via photon exchange. However, gluons are themselves color-charged, resulting in an amplification of the strong force as color-charged particles are separated. Unlike the electromagnetic force, which diminishes as charged particles separate, color-charged particles feel increasing force. However, color-charged particles may combine to form color-neutral composite particles called hadrons. A quark may pair up with an antiquark. The quark has a color and the antiquark has the corresponding anticolor. The color and anticolor cancel out, forming a color-neutral meson. Alternatively, three quarks can exist together, one quark being red, another blue, another green. These three colored quarks together form a color-neutral baryon. Symmetrically, three antiquarks with the colors antired, anti-blue and anti-green can form a color-neutral antibaryon. Quarks also carry fractional electric charges, but, since they are confined within hadrons whose charges are all integral, fractional charges have never been isolated. Note that quarks have electric charges of either +2,3 or 1,3, whereas antiquarks have corresponding electric charges of either 2,3 or +1,3. Standard Model. Fundamental fermions. Evidence for the existence of quarks comes from deep inelastic scattering, firing electrons at nuclei to determine the distribution of charge within nucleons. If the charge is uniform, the electric field around the proton should be uniform and the electron should scatter elastically. Low-energy electrons do scatter in this way, but, above a particular energy, the protons deflect some electrons through large angles. The recoiling electron has much less energy and a jet of particles is emitted. This inelastic scattering suggests that the charge in the proton is not uniform but split among smaller charged particles, quarks. Generations. Mass. Antiparticles. Quarks. Fundamental bosons. In the Standard Model, vector bosons mediate forces, whereas the Higgs boson is responsible for the intrinsic mass of particles. Bosons differ from fermions in the fact that multiple bosons can occupy the same quantum state. Also, bosons can be either elementary, like photons, or a combination, like mesons. The spin of bosons are integers instead of half-integers. Gluons mediate the strong interaction, which join quarks and thereby form hadrons, which are either baryons or mesons. Protons and neutrons are baryons, joined by gluons to form the atomic nucleus. Like quarks, gluons exhibit color and anticolor unrelated to the concept of visual color, sometimes in combinations, altogether 8 variations of gluons. There are 3 weak gauge bosons, W+, W, and Z0, these mediate the weak interaction. The W bosons are known for their mediation in nuclear decay. The W converts a neutron into a proton, then decay into an electron and electron-antineutrino pair. The Z0 does not convert charge but rather changes momentum and is the only mechanism for elastically scattering neutrinos. The weak gauge bosons were discovered due to momentum change in electrons from neutrino Z exchange. The massless photon mediates the electromagnetic interaction. These 4 gauge bosons form the electroweak interaction among elementary particles. gluons. Although the weak and electromagnetic forces appear quite different to us at everyday energies, the two forces are theorized to unify as a single electroweak force at high energies. This prediction was clearly confirmed by measurements of cross-sections for high-energy electron-proton scattering at the Hera collider at DESY. The differences at low energies is a consequence of the high masses of the W and Z bosons, which in turn are a consequence of the Higgs mechanism. Through the process of spontaneous symmetry breaking, the Higgs selects a special direction in electroweak space that causes 3 electroweak particles to become very heavy and 1 to remain massless. On July 4, 2012, after many years of experimentally searching for evidence of its existence, the Higgs boson was announced to have been observed at CERN's Large Hadron Collider. Peter Higgs, who first posited the existence of the Higgs boson, was present at the announcement. The Higgs boson is believed to have a mass of approximately 125 GeV. The statistical significance of this discovery was reported as 5 sigma, which implies a certainty of roughly 99.99994%. In particle physics, this is the level of significance required to officially label experimental observations as a discovery. Research into the properties of the newly discovered particle continues. The graviton is a hypothetical elementary spin-2 particle proposed to mediate gravitation. While it remains undiscovered due to the difficulty inherent in its detection, it is sometimes included in tables of elementary particles. The conventional graviton is massless, although there exist models containing massive Kaluza-Klein gravitons. Although experimental evidence overwhelmingly confirms the predictions derived from the Standard Model, some of its parameters were added arbitrarily, not determined by a particular explanation, which remain mysteries, for instance the hierarchy problem. Theories beyond the Standard Model attempt to resolve these shortcomings. One extension of the Standard Model attempts to combine the electroweak interaction with the strong interaction into a single grand unified theory. Such a force would be spontaneously broken into the 3 forces by a Higgs-like mechanism. The most dramatic prediction of grand unification is the existence of X and Y bosons, which cause proton decay. However, the non-observation of proton decay at the Super Kamiokande Neutrino Observatory rules out the simplest guts, including SU and SO. Supersymmetry extends the Standard Model by adding another class of symmetries to the Lagrangian. These symmetries exchange fermionic particles with bosonic ones. Such a symmetry predicts the existence of supersymmetric particles, abbreviated as sparticles, which include the sleptons, squarks, neutralinos, and charginos. Each particle in the Standard Model would have a superpartner whose spin differs by 1/2 from the ordinary particle. Due to the breaking of supersymmetry, the sparticles are much heavier than their ordinary counterparts. They are so heavy that existing particle colliders would not be powerful enough to produce them. However, some physicists believe that sparticles will be detected by the Large Hadron Collider at CERN. String theory is a model of physics where all particles that make up matter are composed of strings that exist in an 11-dimensional or 12-dimensional universe. These strings vibrate at different frequencies that determine mass, electric charge, color charge, and spin. A string can be open or closed in a loop. As a string moves through space, it sweeps out something called a world sheet. String theory predicts 1 to 10 branes that prevent tears in the fabric of space using the uncertainty principle. String theory proposes that our universe is merely a 4-brane, inside which exist the three space dimensions and the one time dimension that we observe. The remaining 6 theoretical dimensions either are very tiny and curled up or simply do not/cannot exist in our universe. Electroweak bosons. Some predictions of the string theory include existence of extremely massive counterparts of ordinary particles due to vibrational excitations of the fundamental string and existence of a massless spin 2 particle behaving like the graviton. Technicolor theories try to modify the standard model in a minimal way by introducing a new QCD-like interaction. This means one adds a new theory of so-called techni quarks, interacting via so-called techni gluons. The main idea is that the Higgs boson is not an elementary particle but a bound state of these objects. Higgs boson. According to preon theory, there are one or more orders of particles more fundamental than those found in the standard model. The most fundamental of these are normally called preons, which is derived from pre-quarks. In essence, preon theory tries to do for the standard model what the standard model did for the particle zoo that came before it. Most models assume that almost everything in the standard model can be explained in terms of 3 to half a dozen more fundamental particles and the rules that govern their interactions. Interest in preons has waned since the simplest models were experimentally ruled out in the 1980s. Accelerons are the hypothetical subatomic particles that integrally link the newfound mass of the neutrino to the dark energy conjectured to be accelerating the expansion of the universe. Graviton. Beyond the standard model. Grand unification. In theory, neutrinos are influenced by a new force resulting from their interactions with accelerons. Dark energy results as the universe tries to pull neutrinos apart. The most important address about the current experimental and theoretical knowledge about elementary particle physics is the Particle Data Group, where different international institutions collect all experimental data and give short reviews over the contemporary theoretical understanding. Other pages are Supersymmetry, String theory, Technicolor, Preon theory, Acceleron theory. Notes. General readers. Textbooks.